Okay, good afternoon. This file contains the pre-lecture notes for class on Thursday, August 29th, 2013. The relevant reading for these slides can be found in the Carey textbook sections 1.11 through 1.18. The takeaways from this lecture include the remaining general chemistry concepts relevant to organic chemistry. Importantly, this lecture includes general advice to help you draw curved arrows as well as a heuristic to help you compare the relative acidity of organic acids as measured by pKa. So, recall from the last lecture that a dipole moment can exist in covalent bonds between atoms that differ in their electronegativity. Recall from the last lecture that a dipole moment can exist in covalent bonds between atoms that differ in their electronegativity. The sum of the individual dipoles in an atom can create an overall molecular dipole moment. When the center of the positive and negative charges in the aggregate dipole coincide, a molecule is considered to be nonpolar or not polar. However, when the positive and negative charges do not coincide, the molecule is said to be polar. For a molecule to have a molecular dipole moment, the molecule must first include polar bonds, and, more importantly, you must know the shape of the molecule to determine the center of the positive and negative charges to determine whether they coincide or not. Carbon dioxide, for example, has no dipole moment because although it has two polar bonds, as seen here, the overall linear shape results in a net cancellation of the individual dipoles, which are pointing in opposite directions. If we revisit some of the molecules shown in Table 1 of Chapter 1, we can better illustrate the relationship between individual dipoles and molecular shape. Here we see methane with its 4 equivalent CH bonds with dipoles all pointing toward the center carbon. Because each dipole points in the same direction and thus cancels itself out, the molecule has no net dipole. In contrast, water contains 2 polar bonds and 2 lone pairs that do not cancel each other out. The resultant sum of the dipoles produces a net dipole that faces in the direction of the 2 lone pairs, as indicated on this slide by the large black dipole arrow. Similarly, ammonia with 3 polar bonds and 1 lone pair contains a net dipole pointing toward the electron pair. As you review your textbook, be sure that you're able to identify the individual dipoles of each bond and determine whether the net dipole is greater than 0, and if so, the direction that the net dipole points. Throughout the semester, we will be using curved arrow notation extensively to illustrate the flow of electrons in chemical reaction mechanisms. Curved arrows tell us where electrons originate and where they end up when a reaction takes place. Note that these arrows are necessarily curved, never drawn straight, and that the tail of the arrow starts at the electron source while the head of the arrow points to the electron destination. Curved arrows should always begin at an electron pair, or a bond. Curved arrows should always point to atoms or to empty orbitals. Never point curved arrows towards electronegative atoms or electron pairs. For example, if we consider the dissociation of carbonic acid as illustrated here, you will see that the arrow begins at the pair of electrons shared between the H and the O in the covalent bond and terminates at the oxygen. Notice that the resultant products of this reaction have the formally shared electrons localized on the oxygen as a lone pair, where the arrow head pointed to. Also notice that the formal charge of the H and the O have changed given the redistributions of electrons in the products. For practice, calculate the formal charge of each atom in the products and reactants of this dissociation mechanism to ensure that the formal charges are indicated correctly. Note that many reactions you encounter will involve the simultaneous bond formation and bond breakage in a reaction mechanism. We demonstrate this by using multiple curved arrows. In this reaction, the first curved arrow indicates the formation of a bond between oxygen and carbon with the simultaneous cleavage of the carbon-bromine bond. Again, notice how each arrow begins at an electron pair and points to an atom. So here we see the arrow begins at the electron pair in oxygen and points to the carbon atom over here in the other reactant. On the other side, the arrow begins at the bond and terminates at the bromine. Many of the reactions in organic chemistry are examples of acid-base reactions that you already learned about in general chemistry. Recall the three major theories of acid-base chemistry listed on this slide. In this class, we will use only Bronsted-Lowry and Lewis theories to define acids and bases. Although important, the Arrhenius theory was too limited for us to apply to most of the structures you'll see in this course. According to the Bronsted-Lowry theory, in a chemical reaction, an acid is any substance that can donate a proton, and a base is any substance that can accept a proton. Here, the electron pair on a generic base B attacks the H on a generic acid A to create a conjugate acid-base pair. Using curved arrows, we indicate this reaction by starting an arrow at the electron pair on the base and pointing it to the hydrogen atom in the parent acid. This occurs with the simultaneous cleavage of the HA bond, once again indicated with a curved arrow, which begins at the bond between the H and the A and points to the A in the acid, which receives the electrons. The conjugate acid in this reaction is the protonated base, and the conjugate base is the deprotonated acid. In effect, we can say that the acid donated its proton to the base to create the conjugate acid-base pair. Using the Bronsted-Lowry theory of acids and bases, we can see that water is capable of acting as a base when it donates an electron pair to accept a proton from an acid. In this case, a lone pair from a water molecule picks up a proton donated by hydrogen bromide. Using curved arrows, we indicate this by drawing an arrow from the lone pair to the hydrogen with the simultaneous cleavage of the HBr bond, using a curved arrow to show that the bond breaks and directs its electrons toward the bromine. The resultant products of this reaction include a hydronium ion and a bromide ion. Respectively, these are the conjugate acid and conjugate base from this reaction. Water can also act as an acid when it donates one of its own protons to any given base. Here, a lone pair on the amide ion, anion, picks up a proton donated by water, simultaneous with the cleavage of an HO bond in the water molecule, producing the resultant products of ammonia plus hydroxide ion. Once again, we indicate that here we have a conjugate acid and a conjugate base. We can determine the relative strength of an acid using the value of pKa, which is calculated from each acid's equilibrium constant, as shown here. By examining the formula for Ka, we can see that higher Kas indicate more protons are donated than lower Kas. Thus, larger Kas indicate strong acids and small Kas indicate weak acids. By definition, then, as pKa decreases, acid strength increases. In general, we reserve the term strong acid for those substances that have pKa's lower than hydronium ion. As you can see here in this chart, the acid strength increases as we move up the slide, with the resultant pKa decreasing. We reserve the term weak acid for those substances that have pKa's higher than hydronium ion. As seen on this slide, acid strength is decreasing as we move down the slide, concurrent with increasing pKa. For additional information about the relationship between pKa and acid strength, see Table 1.8 in your textbook. Remember that due to the relationship between an acid and its conjugate base, the stronger an acid, the weaker the conjugate base. As shown here, Hi is a stronger acid than HCl, but the chloride ion, Cl-, is a stronger base than the iodide ion, I-. This semester, it is not expected that you memorize the pKa's of many different compounds that are shown in your book. However, you should know the relative pKa's of the important functional groups that are shown here on this slide. Other pKa values that are important to understand organic reactivity will be introduced throughout the semester as we need them, but for now, you should work to memorize the relative pKa's of the functional groups that you see here on this slide. When the pKa of an acid is unknown, it's possible to determine the relative acid strength based on the structure and the electronic environment within a molecule. There are 6 major factors that affect acid strength that are shown here on this slide. First, inductive effects are related to the electronegative atoms that are within 3 to 4 bonds of an acidic hydrogen atom. Second, the size of the conjugate base that forms after the deprotonation of a parent acid. Third, hybridization of the conjugate base that forms after the deprotonation of the parent acid. Fourth, aromaticity in conjugate bases that form after deprotonation of the parent acid. Fifth, any resonance contributors that exist for the conjugate base that's formed after deprotonation of the parent acid. And lastly, the electronegativity of the atom that is directly bonded to the protic acid in the parent acid. Alternatively, this can be thought of as the electronegativity of the conjugate base itself. Some students find it helpful to remember these 6 factors by using the simple mnemonic at the top of the slide, I share, which just has in order induction, size, hybridization, aromaticity, resonance, and electronegativity. For now, we will examine 4 of these 6 effects: induction, size, resonance, and electronegativity, returning to hybridization and aromaticity later on in the semester. First, we examine the inductive effects, which refer to the induced dipole created in a molecule by electronegative atoms that are within 3 to 4 bonds of an acidic proton. Compare the relative pK of ethanol and 2,2,2-trifluoroethyl alcohol, shown here. The higher pK of ethanol indicates that it is a weaker acid than 2,2,2-trifluoroethyl alcohol. But why is this the case? If we examine the Lewis diagram for 2,2,2-trifluoroethyl alcohol, we can see that the fluoro groups create an inductive effect by drawing the electron density away from the acidic proton, which leaves it more susceptible to an attack by base. In the Lewis structure, this is indicated by the symbol indicating a partial positive charge on the acidic proton and a partial negative charge on the side of the molecule containing the fluoro groups. Notice that each of the individual dipoles point in the direction of the fluoro groups, drawing electron density away from the acidic proton. In effect, it's easier to remove this proton in 2,2,2-trifluoroethyl alcohol than it is to remove that same proton from ethanol. The second factor we will consider includes the size of the conjugate base, which also affects the acidity of the parent acid. In general, as the size of the conjugate base increases, the strength of the parent acid also increases. Size is the most important factor for comparing the relative acidity of acids that are derived from the same group or family in the periodic table. Note here on this slide that HI is the strongest halo acid, as the size of its conjugate base, I-, is larger than those of the other halo acids. But why is this the case? Remember from Vesper theory that electrons repel one another, attempting to achieve the maximum distance between each electron. As such, the larger the conjugate base, the more space there is for electrons to distribute themselves at a maximum distance. On smaller conjugate bases, the electrons are closer together, and thus the conjugate base is destabilized, which weakens the strength of the acid. In some sense, you could think that the acid prefers to stay protonated than deprotonated, given the destabilized conjugate base. The third factor we consider is electronegativity. The electronegativity of an atom bonded to the acidic proton affects the acidity of the parent acid overall. In general, as the electronegativity of this atom increases, the strength of the parent atom increases. Electronegativity is the most important factor for comparing the relative acidity of acids that are derived from the same row in the periodic table. Note here that HF is the strongest period 2 acid, as the electronegativity of fluorine is greater than those of the other row 2 acids. But why is this the case? Remember that electronegative atoms draw electrons toward themselves. As such, the greater the electronegativity of an atom bonded to a proton, the less electron density there is around that proton. As with inductive effects, it's thus easier to remove a proton that's attached to an electronegative atom than it is to remove a proton attached to an electropositive atom. Remember, size is the most important factor when comparing acids in the same group or family, and electronegativity is the most important factor when comparing acids derived from the same row of the periodic table. Finally, resonance also contributes to the strength of an acid. The more resonance contributors that exist for a conjugate base, the stronger the parent acid. Compare the two acid-base reactions here on this slide. Notice that the pKa of water in the top reaction is greater than the pKa of nitric acid in the bottom reaction. This indicates that water is a weaker acid than nitric acid. In both cases, the protic acid is attached to an oxygen, but in nitric acid, the proton is much easier to remove than it is in water. The reason for this can be attributed to the fact that the conjugate base of nitric acid has 3 resonance contributors, but the conjugate base of water has no resonance contributors. In effect, the electron density is more spread out or delocalized in the conjugate base of nitric acid than it is in the conjugate base of water, thus making nitric acid a stronger acid. Once again, delocalization, or the spreading out of electrons through the resonance structures, increases the stability of the conjugate base, making it a much more stable structure. In general, when you're attempting to determine the equilibrium position of any acid-base reaction, you can assume that the equilibrium will shift in the direction of the weaker acid. This is because the stronger acid is better able to donate its protons than the weaker acid. We indicate this in a chemical equation using equilibrium arrows of different length. The longer arrow indicates that the equilibrium is favored towards the right side of the reaction that's shown here. If we look at specific examples of strong acids, we can see that the equilibrium of this reaction is to the right because the hydronium ion in the right is a weaker acid than the hydrogen bromide acid on the left. We can see this by comparing the pKa's. Note that the pKa of hydrogen bromide is less than the pKa of hydronium ion, which indicates that hydrogen bromide is a stronger acid. Thus, the equilibrium lies to the right. In this second example, we can see that the equilibrium lies to the left because acetic acid on the left is a weaker acid than hydronium ion on the right. Once again, compare the pKa's to determine the relative strength of each of the acids. Remember from this lecture 4 important points regarding Bronsted-Lowry theory. 1. A strong acid is one that is stronger than H3O+, and a weak acid is one that is weaker than H3O+. 2. A strong base is one that is stronger than OH-, and a weak base is one that is weaker than OH-. 3. The strongest acid present in significant quantities when a strong acid is dissolved in water is H3O+. And 4. The strongest acid present in significant quantities when a weak acid is dissolved in water is the weak acid itself. These points will become increasingly important as we consider different organic reaction mechanisms throughout the semester. At a few points in this semester, we will also use Lewis' theory of acids to explain some reactions. Unlike Bronsted-Lowry theory, which focuses on proton donation, Lewis' theory focuses on electron pair donation. According to Lewis' theory, an acid will accept an electron pair while a base will donate a pair of electrons. This definition works readily to identify all of the acids and bases we have seen on the previous slides. More importantly, in addition, Lewis' theory allows us to identify acids and bases in all compounds that do not contain hydrogen atoms. Recall that Bronsted-Lowry theory requires us to define acids and bases in terms of who donates a proton and who accepts a proton. Lewis' acids and theory does not. Regardless of whether H is present, all compounds contain electrons. As such, any compound can readily be labeled as an acid or a base using Lewis's theory. Note in all 4 of the schemes listed here on this slide, the generic base, indicated with a B, donates its electron pair to the generic acid, indicated with an A, which accepts that pair. Thus, we can label neutral or ionic compounds as Lewis acids or Lewis bases with no hydrogen needed at all. That's all for today's pre-lecture. As always, be sure to review the relevant reading in the Carey textbook and come to class prepared next week to apply what you have learned.